Now let's very quickly go, and now my job is easy because now I can just say artificial potential field without caring about how will you implement it up. I'm not going to speak about it, and therefore I will discuss a number of behaviors. However, the answer to everything will be artificial potential field. So let's go one by one. The first behavior is what's called as aggregation. And the aggregation behavior is when initially the robots are dispersed. They all say that our country is into problem. We need to act upon it. We are one team. Everybody come. There are two ways to aggregate. One algorithm that you use that's completely centralized, that one person decides where to give dharna, where to come and aggregate, but then we cannot do that over here, that's centralized. So the answer is of course potential field. Or social potential field, where every robot attracts each other. So every robot attracts each other. And that's simple. And this attraction is primarily now I'll let you figure out why effectively all the sensing discussed so far are local. Light from a faraway robot will get occluded by so many things, so many other robots, it's not going to reach a faraway robot. Sound, faraway robot is going to be so weak that it will be filtered out. You anyways look at only the sounds which are significantly high and the robots which are significantly close. So it's local sensing. So I primarily see only the near robots and not the faraway ones. So I basically go to the nearest robot. Now, and that's exactly what will happen. So let's do it around over here. The nearest to these are these two. So I go intermediate between them. For this robot, nearest are these two. For this, these two are the nearest. Then for this, probably that is the nearest. For this one, this is the nearest. For this one, it is this as the nearest. For this one will probably follow here. And this one, I think, is likely to be going here. And next time what really happens is that this robot is sufficiently here, this is here, this is here, these two are here. I cannot draw them too close because they are sonar sensor that are avoiding collision. So now this one follows here, this one follows here, this one follows here, this goes here, this goes here, and these are into equilibrium already. So what really happens is and now no robot is going to move. No robot is going to move, so that means they don't aggregate, they cluster. And that's exactly what will happen. Create a simulation program, make every robot go towards the nearest robot. And once you make every robot go towards the nearest robot, they are going to cluster around like this over here, which means that this rule is actually false. This is bad rule. And there's actually nothing that I can do about it. If there was communication, I could have queried on the number of clusters, location of the clusters, and made rule accordingly, but I cannot do that. Each robot has a local sensing, so this robot doesn't even know about all these. This robots don't even know about all this. These robots don't even know about all this. When you don't know about the other robots, what are you going to do? Now, in my course on motion planning, robotics super specialization, we deal with a lot of these issues, but we have a lot of high quality sensing and everything available with us. Here, for every problem, I'll have just one solution, randomization. So that's what we do. So that's your artificial potential field or social potential field. And what you do, sometimes you have a random behavior. For time t. So for t time, you display random behavior and then you display a potential field behavior. And here, of course, the transition from potential field to random behavior happens with a certain probability, with a small probability. So normally I just, and that's also where I init. So normally I just display artificial potential field behavior. So, but then with a very small probability, I go to a random behavior, and for t times, I just display a random behavior. And therefore, what will happen is, even if this equilibrium was reached, it's an infinite behavior. There's no terminate. It'll go as long as the battery support. So after some time, what will happen is this robot will go on a tour around over here, and then again it will get attracted over here. Sometimes this robot will go on a tour over here and it will get attracted over here. Sometimes this robot will actually go on a tour over here, and now it can sense these robots, so it goes here, and now the closest to this is both these two, so it actually turns up and turns around over here. After some time, this robots will go around on a tour and come back, go around here and come back, go around here and come back, go around here, and then it can see this one and go here, and then this will go on a tour and come back, and then this will feel the attraction, so this one will go more around over here, and they will join as one cluster. Now, again, a weird theory that I give, which is theoretically correct and practically wrong, is that as time tends to infinity, this really means infinity. Number of clusters tend to what? That's exactly the same why I said what I said in potential field as well. So we had a equilibrium condition like this and a bad equilibrium condition like this, and the robot was stuck over here, and this was the goal. So attraction to goal, and these forces cancel each other. There I said it'll go on a random tour, come here, tour, go, come here, tour, come here. Along with time, the length of the tour will increase. The length of the tour will increase. The length of the tour will increase. It'll get increased even further. It'll get increased even further, and then it'll go. So it can actually overcome any obstacle like this. And I said as time tends to infinity, it will eventually reach to the goal because it will overcome whatever obstacles comes on its way, and it may get up into a worse situation, but sometimes it'll get into a better situation as well. So the probability that it reaches a goal at any point of time is non-zero, and therefore as time tends to infinity, the robot always goes to goal. The same thing is around over here. At this equilibrium condition, if you look at any robot over here, let's say R1, so and t is sufficiently large, so I say some control sequence exists that takes R1 out of current cluster and into another cluster. that, so there's at least one control sequence and it is actually true that this is the control sequence. It takes out from this clusters and it gets out into this another cluster. Now the robot is taking the store multiple times because with probability P it goes here every single unit time. So that means if I run the simulation for delta times, or delta is the total number of iterations, then P into delta times, it will take random sequences of length t. And delta is infinite. I run the simulation till infinity. Now, because this behavior for infinite simulation will be invoked infinite times, at least in one of those infinite times, I'll get exactly the sequence. And because at least in one of those infinite times I'll get this sequence, that means the robot will actually come in over here and strengthen this cluster. Now, a cluster cannot break because once all the robots are into one cluster, even if they leave, where are they going to come? There's only one cluster, they'll come around over here. So that means there's a non-zero probability that all robots come into one cluster. I can repeat this for every robot. That means as time tends to infinity, all robots will, with non-zero, because there's a non-zero probability that all robots leave their clusters and join any one cluster, because it's an infinite simulation, at one time all the robots will be in one cluster, and because of that, once they are into one cluster, that means no matter how long you run the simulation, they're never gonna leave the cluster. That's the behavioral finite state machine for that. I start over with this behavior and then based on this condition I made this transition. These are the probabilistic or random transition and this is the timed transition. So fair enough, that was aggregation. Let's discuss the other behavior quickly, which is dispersion. So these are what the robots are. Initially, they want to go as far away as possible from each other. And that's exactly what happens. So finally, they are nicely distributed far away. And the logic is obviously simple. The answer is again a social potential field. And my mantra is all robots repel each other. There's no attraction. All robots just repel each other. And we say it saw multiple sensors from which repulsion can be effective, so we cannot do that. Now there is another form of dispersion that says with communication constraints, what really happens is if I unbounded map, the map is of course unbounded, the boundaries were just to show it to us. If you let the robots go far off, they will really lie far off. Now, an interesting question could be why not they just go infinity? If you simulate it up, they'll actually go up till infinity. This robot will feel repulsion from this, and this, and it'll go here, and it'll keep on going till infinity. They'll not go to infinity because they all have local sensing. So after some distance, A, the repulsion force becomes extremely weak. B, it cannot actually sense this robot by any of the sensors. The sound signals that we talked about, it's too weak to be really effective. Now, but then what happens is that sometimes even this is bad because we forgot that there was a mobile ad hoc network and the network links have broken because of the distance. The robots cannot communicate over this thing. So every Bluetooth has a range. It does not work after that. And because of that, sometimes what you say is that The robots will not move around unless their signal strength is less than a distance, which means if the current distance is greater than threshold, then it will, here it could try breaking up this because it is still connected to this one, but in this case it will not try this thing because the wireless ad hoc sensor network will break. And because the wireless sensor ad hoc sensor network will break, it needs to be always under communication. That means it must always stay intact. So that puts a limit that no robot goes more than a threshold, where this is the distance threshold is, of course, a little less than the communication threshold. Just a little less than the possible communication threshold that the robot has. So that's actually an interesting application. So the robots go as far away as from each other as possible, and while they do go as far away from each other as possible, they still maintain a communication with each other.